Hello and welcome to today's webcast brought to you by Laser Focus World. Today's event, a tunable LED light source for camera and image calibration, will be presented by Trevor Vogt, Director of Engineering at Gamma Scientific. This presentation is both live and interactive, so you can ask questions at any time by clicking the Ask a Question box in the presentation window and clicking the Submit button. And we do encourage questions. We will hold a Q&A session right after Trevor's presentation. For those in the audience who want a copy of today's slides, a PDF of today's presentation is available in the Event Resources section below the Q&A box. If you are running pop-up blocking software, you will need to disable it to view this webcast. In addition, it is recommended that you close down all other applications for better performance. For your convenience, this presentation will be available on demand within 24 hours of this live event. A reminder email message will be sent to all registrants with a link to the archive. It will also be accessible from our homepage at www.laserfocusworld.com. Today, we also have two short interactive polls during the webcast that will give the audience a chance to participate in providing information. And in fact, we're going to hold the first one right now. And it's being pushed out to you. The question is, what is your primary application or interest in attending this webinar? And the answers that you can choose are 1, camera package module image sensor calibration, 2, wafer level sensor calibration, 3, microscopy fluorescence biology, 4, test and calibration standard light source, and 5, other. So we'll take a few seconds and you can enter in your answers, and then I'll just mention a little bit about them, then we'll get started with the webcast. So it looks like test and calibration of standard light sources is the most popular application that you're interested in, followed by camera and package module image sensor calibration. And third is other. So that's probably a lot of interesting things in that other category. So with that, now let's get the webcast started. It gives me great pleasure to introduce our presenter, Trevor Vogt.
Hello, everyone, and thank you for joining us today. We're going to be going over some general overview of our new product, the SpectralLED Tunable LED Light Source, what we also refer to as a Model RS7. So I'll just get started and tell you a little bit of a background about Gamma Scientific. We've been around for over 50 years, founded in 1961, and we're a leader in light measurement and precision measurement systems. So we manufacture products for a variety of markets, including LED segment, display measurement, image sensor, test and calibration. We also have a highway safety line and a full test and calibration laboratory here. Everything we do is based in our factory headquarters here in San Diego. Gamma's broken up into a few business subdivisions. It all kind of centers around our NAVLAP ISO 17025 accredited calibration. We make spectroradiometer measurement solutions. We also make photometers, radiometers, test and calibration lamps, including the LED light source that we're going to be focused on today, and then the highway safety product line. And we're really going to just be focused in today on our calibrated tunable light sources. We also have historically made 1,000-watt FEL lamps for tungsten halogen-based standards, and we've made a wide variety of different types of uniform light sources, going all the way up to satellite sensor calibration applications. The tunable light source specifically, we've been manufacturing some variety of this product for over 15 years now. We first introduced it in 2001 with a single color, what we called then an RS5. It is used as a calibration reference light source and allows you to digitally control the brightness output with a linear constant current driver. Very quickly it became apparent that customers needed more than one color, and we started getting requests to package multiple of these optical heads into an integrating sphere. From there, we went into the next generation of the product, the RS5B. This actually combined 10 channels into a single device and gave us our first application where we were actively mixing different wavelengths of LEDs to create a broadband spectrum. These sources were great because they don't have hardly any downtime using the LED-based illumination, and they were all computer controllable, which allowed for easy integration into other production lines. So what we've done now is we've taken all the knowledge and information that we've learned over the years from those previous generations of light sources, and we've integrated it all into a brand new product, which has been designed completely from the ground up. We have a unique design which allows us to independently control 35 discrete optical channels. So those are LEDs which have a physically different color, and each of those channels is controlled with a digital control with 16-bit resolution. So what that translates into is a very, very small step size if you're adjusting the brightness output. Each one of those channels is a pure DC constant current circuit, and its floating differential sensing allows it to not have a single ground reference, which means there's no crosstalk between different channels. Each one has its own floating individual ground. We also have a built-in thermal controller with a high-power Peltier cooler. This allows us to keep this large array of LEDs temperature stabilized, even when we're working at very high drive currents and output powers. And there's also an optical photodiode for real-time feedback to maintain the amplitude and regulate the output. This shows the 35 channels that go into our standard design. So as you can see, there's very, very dense spacing throughout the visible spectrum. We have a unique channel roughly every 15 nanometers in the visible and about 15 nanometer spacing in the near infrared. That corresponds roughly with the full width half max of those LEDs, so there's no gaps in energy anywhere in the spectrum from 380 nanometers all the way out to 1,000 nanometers. And as I mentioned, each of these has an individual constant current driver with its own control on the output power. So at this point, we're going to briefly break and go to a short video demonstrating in real time the software and also showing beside that a small light box with a few props inside of it. This video shows the RS7 running through a brief demonstration mode. So we begin just by turning on each channel individually, cumulatively summing up all the 32 channels. And then we're going to move through a monochromatic sweep mode where one channel is illuminated at a time. This produces some really lovely fluorescence in the lower wavelength ranges and shows how different illumination colors are going to impact a Macbeth color chart in the visible range, for example. Then we move into some spectral simulation modes where we show broadband illuminant matching, here an illuminant E, going into a black body, illuminant A, showing that warmer color temperature, showing a D65 spectrum with the very cool color temperature. And in each of these cases you can see how it impacts the different samples that are being illuminated here. Thanks for your attention. Okay. Now I'm going to move into a little bit more just on the technical details and system overview. So main component, which is behind the kind of the brains of the device, is our main board, which contains the microcontroller. All of the spectral calibration is built into the microcontroller itself, so the device is self-contained. And this also has the 64 constant current drivers that we have, electrical constant current drivers to drive those 35 optical channels. Then we have our LED PCBA. It's comprised of over 100 surface mount LEDs, Many of the different channels are doubled or even tripled up so that they're radiometrically equal in power to some of the brighter LED channels. So over 100 dyes to create these 35 optical channels, and it's all on a very high power temperature stabilized Peltier cooler. Then it's coupled into different variety of output optics. Our standard model is coupled to an integrating sphere and provides a uniform radiant output port, but we have quite a variety of different models available which give you different optical configurations. And then there's the application software side of it, which allows you to control the device. And we also have a full API, which I'll get into a little bit later, which allows for simple integration if you're writing your own software package and using this with other devices. So one of the major capabilities that this device boasts is the spectral simulation. And what we're able to do is combine each of these individual LEDs in very specific ways to create and simulate broadband spectra. So what you can see here is the blue curve on these plots is our target spectrum, and the white curve is the actual output. And then the LEDs that comprise that white spectrum are shown underneath. And basically, by summing all of these LEDs up, we're able to reproduce the broadband energy in a very accurate way with low RMS errors. It allows us to hit very specific color coordinates if we need to, or optimize the fit for the best spectral match. So some of the major advantages of using this LED-based light source, certainly the lifetime is probably the biggest advantage in terms of minimizing downtime and optimizing the system's stability over a long period of time, with over 20 times longer than standard tungsten halogen light sources. And in fact, it's probably more like 200 times longer in many cases. For tungsten halogen light sources, the calibrated period is typically never specified for more than 100 working hours. So in this case, we expect the light source will work for over 10,000 hours, probably greater than 40,000 hours in many cases, continuous LED on time. And we've had very little failures in the previous generations of these products, so we're confident in the high reliability and the robustness of these LED-based sources. And it's self-monitoring and self-adjusting, so rather than a traditional tungsten lamp, which you would drive with a constant current circuit, that's open loop, so the lamp is never completely stable and it always has some delta from the calibrated value. In this case, we have an optical photodiode built into the system which is monitoring in real time, such that we can make minor adjustments to the constant current driver and maintain the optical output within a fraction of a %. So that allows us to maintain a much higher accuracy and repeatability than what you could with traditional sources. It's obviously much more versatile, so rather than giving you a single black body curve at 2856 Kelvin, now you can generate any type of curve you want, whether it be black body, a CIE illuminant, or a spectrum you measure on your own and simply import into the device. And it's going to maintain the color accuracy over the entire range of output levels. So now you have adjustable amplitude and adjustable color temperature all built into the same source. Or you can even use it one channel at a time if you want to just illuminate a device with monochromatic light or quasi-monochromatic light. You could turn on a single blue channel and see its response to the blue. It's much faster than a tungsten halogen source. Rather than waiting 15 minutes for it to warm up or stabilize, we can switch between spectra within 5 milliseconds, and the optical feedback is fully regulated within 50 milliseconds. So the amplitude is 100% stable and repeatable to within that fraction of a % accuracy within that 50 milliseconds. So switching time allows you to quickly go between different power levels or between different spectrums. No filter wheels, no ND filters, nothing like that. It's all solid state, no moving parts anywhere. It's much brighter as well, so using these high brightness surface mount LEDs allows us to achieve quite a lot of energy. Most of which are able to be driven with up to an amp of drive current, and with those 100 dyes on the board, you can imagine that when you're driving all of them at high power, we're generating several watts of optical power. And in terms of the actual usable output at the end of the mixing In our standard configuration with an integrating sphere, it's brighter than 60,000 nits when outputting D65 illumination, so extremely bright. And the cost, lastly, is going to be lower, especially when you consider the long-term durability and uptime that it's going to help you maintain. No needing to replace lamps, and you can also trust that the output is stable because it's self-monitoring. There's no doubt if there's any drift or any sort of system error has occurred. Because we have the optical feedback built in, we're going to be told in real time via an alarm if any given channel is no longer functioning or is not outputting as much energy as we expect. We can pull that type of information from the firmware. And obviously, the versatility adds to the lower cost or the higher value, because rather than needing multiple sources for multiple applications, you can use this single source and configure it for a variety of different applications. So the advantages as we see them are simplifying your calibration process, improving accuracy, reducing the cycle time by using our fast switching, and being able to quickly simulate a huge variety of different light sources, all by maintaining a constant CCT. So we can do things like simulate a CIE illuminant or X-Rite color patch under different illuminant conditions, or as I mentioned, you can import your own spectrum that you've measured with an external spectroradiometer. Very simple format to import your own data there. So with all the LEDs powered at maximum, I have over 500 watts of LED power. That's electrical and optical power that is being dissipated by the system. And the maximum radiance at D65 is greater than 30,000 microwatts per centimeter squared per steradian, and as I mentioned, 60,000 nits. And we are able to provide between 3 and 4 decades of dynamic range using those 16-bit DACs. So every individual color has 65,000 steps for intensity control. And you can imagine if you combine multiple channels together, you can have even more dynamic range or resolution. But for a given fixed spectrum that you're not trying to do anything where you're combining channels, you can get roughly 3 to 4 orders of magnitude of dynamic range. And in the case where you really need more than that, we do have options available where you can couple an ND filter to the output, or we have a ND or a stepper motor controlled iris, which is available as a standard option as well. So that allows you to even further increase the dynamic range in applications that need it. So this is talking a little bit about our spectral synthesis engine. So the RMS fitting is actually built into the device itself. It doesn't rely on any sort of GUI or this Windows-based software. The firmware itself performs the spectral fitting, and it allows you to import any arbitrary target spectrum or choose from a variety of presets that we build into it, including CIE illuminants. You can convolve color patches with illuminants. Basically, any target spectrum you can send it, the device will take its best possible attempt at fitting it. And in many cases, we find the fit to be below 20% RMS error, and in some cases even below 10% RMS error for, say, a black body curve. The fit is very, very accurate. The interface is very simple. We have a RS-232 serial control, so if you're writing your own software, it's just sending ASCII commands. And you can configure it for different optimized conditions, whether you want to minimize the RMS error or to hit a very specific CIE XY coordinate. We can actually minimize the delta E to 0 and always hit a given XY coordinate and optimize the fit that way. So here we're showing an illuminant E basically fitting to a flat line from 380 all the way out to 1,000 nanometers. So you can see the fit in the visible and the infrared here in this slide. Again, the blue curve being the target and the white curve being the actual output of the device. So now I'm going to quickly move to a brief live demonstration where I have the software and a SpectralLED device plugged in real time. So give me 1 second while I get the screen sharing set up and broadcasting. Okay, so hopefully at this point you can all see my screen. So what I have here is our software package that we provide with the device. This is a Windows-based application, although the device can be used on any sort of operating system. We have drivers available for OS X, Linux, and for Windows. So what I can do within this software package is quite a lot. Basically, we have an interface here at the bottom, which is we equate to an equalizer. So I have individual control over every single channel on the device. And then I have the ability over here in the target spectrum area to load in different arbitrary spectrum and fit to it. So right now I have on the screen just a black body curve, a 2856 radiator, and I fit to 2000 candela. But in real time I can go ahead and start adjusting the spectrum if I want to, and you can see I can just add a little blue or a lot of blue and start to tune things that way if I wanted to. Individual channel control here is quite simple. You can just bring up, any sort of color that you want, as simple as dialing it up on the equalizer here. And in real time, it's always going to be reporting our output power in terms of radiance and in luminance. If it's a black body type of spectrum, it'll give you a CCT and the color coordinates. All of these parameters are changeable, easily adjustable by a user. So I can quickly go down to a low power level, bring it up to a higher power level. And the calibration knows basically how much energy each channel has integrated under the curve. So you can work easily in radiometric or photometric units without having to keep track of the spectral power distribution. The calibration is also very thorough in that we characterize every channel at a variety of power levels. So we don't just take a single scan and assume that it's always the same. We know the LED has some wavelength drift as a function of drive current, so we characterize that and build it into the device. So on this green channel, you can see that in particular because the green, this particular wavelength has a decent amount of drift as a function of drive current. So here at a low power level, you can see it's at about 542 nanometers. As I drive it up, it's actually going to blue shift all the way to about 530 nanometers. So that's all built into the device, and as a user, it's very seamless, so you don't have to think about these type of things. If you're fitting to a given target, like a luminant A, it knows the exact contribution each channel makes at the given power level for the spectrum, and it's going to actually iteratively solve this process so that we're actively considering the power level of the drive current when we do our spectral fitting. We can also do things like arbitrarily color correct the spectrum. So here we have this starting black body curve. Anywhere within the gamut of the device, I can just click and it's going to fit to that color immediately and give us that output at that particular color coordinate. Same goes if I want to input the value here as a text. I can do that as well, color correct, or set a given target color temperature. Now I've color corrected my luminant A to be a 5000 K spectrum, or I can arbitrarily just generate a black body curve with any sort of color temperature. So quite a lot of power in the device, very flexible. The other feature that we build into this is the ability to take a given illuminant and convolve it with an X-Rite color checker. So here we can see what the foliage color patch would look like illuminated under illuminant E. So here you can see it's kind of a nice green color, and if you were to take that same color patch and put it under illuminant A illumination, now you're going to get something quite a bit more yellow because of that really warm color temperature of the halogen lamp. So really powerful tool in allowing you to quickly do these type of simulations. And this is primarily intended just to get our customers started and give you a quick and simple tool to start generating spectrum. Everything I'm doing here can be done through a terminal, a hyperterminal type window, or by writing your own software and sending simple ASCII commands. In real time, we're actually demonstrating the commands that we're sending to the device at any given moment, so you can start to kind of see exactly how controlling the device via the API would work, setting the units, setting a channel power level, looking at responses, and it's all very well documented in our manual how to write your own software. It should be quite straightforward in our perception. So I think that gives a good overview of the software, and potentially if we have questions at the end, we can talk a little bit more about it. One more thing I'll briefly mention is just we allow you to choose quite a bit of different units if you need to, 10 degree, 2 degree, photometric units. You can also change from a Radiance source built into the firmware. We can actually, for our standard device, which is an integrating sphere with a radiant output port, we can actually move it into an irradiant geometry just by specifying a working distance as a user, and it's going to automatically scale all your built-in calibration to be in units of illuminance and irradiance rather than radiance and luminance. So now we can find out exactly how much energy we would have, say, at 50 centimeters if we were fitting the same spectrum. So if you have a bare sensor or a lens sensor that you're testing, it's going to work for both of those type of applications with a single device. I'm going to go back to the presentation now. Give me 1 second. Okay. So here is just a brief overview of all the included spectral presets that we give you with the device, all the CIE illuminance and X-Rite color checkers. And as I mentioned, this is just kind of a starting point. We fully expect that in many cases customers will want to import their own spectrum, and we make that process very simple. This is just a little overview of the control API that we provide with the device. So the interface provided is we have a USB port, and we also provide a DB9 connector. The USB is a virtual COM port, and the particular provider of this hardware that we use allows us to provide drivers for Windows, OS X, and Linux, or using the RS-232 interface, you can actually control this with any sort of simple microcontroller or integrate into a PLC-based system. All of the spectral calibration is built into the unit, so all of that data is readily available even if you don't have a computer interface with the device. You can basically send a target spectrum to it using a command TSP followed by the array of data, and then do a fit with the command FTS. So all 3-letter ASCII commands, some of which have operators, numeric operators afterwards, and all of the algorithm for spectral fitting is also built into the firmware. So again, this device is completely self-contained and doesn't require any external data or software package in order to run it. And it's important to note that every single unit is individually calibrated and characterized, and the unit-specific data is what's being stored into the unit. So we're not making any assumptions about anything from unit to unit in terms of LEDs or power level response. Everything is individually calibrated so that it ensures absolute accuracy. And that all gets back to our NAVLAP accreditation. So our ISO 17205 calibration laboratory gives us absolute traceability to NIST, so that everything we do has very low uncertainty, and you know that you have an absolute reference standard which you're traceable to. That applies to both the wavelength scale and the amplitude scale, whether we're providing a unit for radiance or irradiance geometries. And it's provided with each unit. It really is kind of the backbone of the functionality. Without this powerful calibration and without the data, the device wouldn't be as powerful as it is. So we're pairing the hardware capabilities with the software and firmware capabilities and with the calibration and the accreditation accuracy. And again, those pure DC constant current drivers coupled with the optical feedback ensures that we're able to provide a radiometrically stable output within less than 0.1%. And our absolute traceability to NIST is an uncertainty of plus or minus 1%. So absolute accuracy within 1%, but the repeatability and stability much better, even a fraction of a percent. So quite a few different applications for this product. The primary application that we've seen is camera and image sensor calibration, whether that be CCD, CMOS, or even just classical silicon photodiodes, single pixel essentially. Also wide applications in ambient light sensors where you might have a RGB, potentially a fourth channel there as well. Depending on what stage in the manufacturing process you're in, you might be at the sensor level or testing an OEM camera, which is including the electronics in that sense. So testing your own electrical design, potentially using an off-the-shelf sensor, or if you manufacture the sensor, testing it more at a wafer level potentially. We can also use this fluorescence excitation or microscopy applications, infrared sensors, fingerprint sensors, quite a few different applications there, going into even photography and cinematography applications as well. So moving into that, it's more specifically the measurement applications that might be of interest are things like white balance, quantum efficiency, pixel defects. Many of our customers use it for a flat field calibration with the uniform output port. Linearity is another very important one because we are able to provide such a wide dynamic range. Responsivity, sensitivity, these are all very important parameters for many people to characterize, again, whether you're at the sensor level or testing a fully packaged electrical camera system. So at this point, we're going to briefly go to our second polling question, which just asks a little bit more about which application is most interesting to you.
Yes, this is John, the moderator. This is the second interactive audience poll. And yes, the question, what measurement application is your primary interest? Your choices are dynamic range, spectral responsivity, linearity, flat field calibration, or other. So we will take a few seconds and wait for the audience to answer, and then take a look at the answers. Actually, we have two questions here. This is the first of the two questions. And looks like for the first question, which measurement application is your primary interest, it looks like spectral responsivity has gotten the most votes other than the other category, which I think probably holds, oh, well, results are changing. So it looks like spectral responsivity is getting the most answers here, followed by the other category in flat field calibration. And the second question we have, looks like people have responded to already. What area are you interested in? And the possible responses are R&D, production, or other. And R&D has by far gotten more of the answers. So this is a very R&D heavy crowd, although production is quite important too. And with that, I will pass this back to Trevor.
Thanks, John. So now we're going to get into a little bit more specifics about the different optical configurations that we provide. So the core electrical and optical, or the core electrical engine with the LED drivers and the thermal control, the optical feedback, is basically the heart of the device, and we can couple it into a variety of different optical output configurations, different ways of mixing it for providing irradiance or radiance, or even potentially total luminous flux. We've gotten quite a variety of different inquiries for different sorts of applications. So what we've done is we've basically created 5 standard models that we offer, which cover a great variety of the applications out there. Certainly if there's some adaptation or customization that's needed, we're always willing to have that discussion and give you some sort of proposal. The main configuration, or our standard configuration, is what we call an RS-7-1. Has a built-in integrating sphere with a 200 millimeter and a 75 millimeter output port. That 75 millimeter output port is able to provide a uniformity greater than 97% over the entire 75 millimeters. If you consider only the center 50 millimeters, it's actually closer to 99% uniformity there. So depending on just how large of an area you need for your flat field calibration. The nice thing about this, as I mentioned in my demonstration, is it allows you to easily switch to an irradiance geometry. So rather than just having this radiant output port for a lensed camera system, now you can input your own working distance and essentially use this as a point source, assuming you have enough working distance, and use it in an irradiance mode for a bare detector, a system which is not lensed. So really convenient in that it allows you to kind of jump back and forth between those different optical geometries just with our standard model. We have a few upgrades for that. There's the motorized stepper iris. So that particular configuration assumes that you're probably working in an irradiance geometry, and you can step down the diameter of that port. And that allows, it's all integrated into the firmware, so controlling the size of that output port via the stepper motor is just another simple ASCII 3-letter command that you send the device. And in that mode, the calibration automatically scales based on the known size of the iris. So again, all of that power and intelligence is built into the firmware so that you don't have to keep track of that as a user. You just set your iris size. You know, maybe you're changing your F number, and then the calibration automatically scales so you know how much irradiance you have at your given working distance. And then we also have the wavelength monitor system. So this is a very unique solution that we provide, which actually builds in wavelength monitoring capabilities. In addition to amplitude feedback is always included with every model, but this gives you one more layer of monitoring where you can actively tell of a single LED channel has changed any in wavelength since the calibration time. And this particular approach actually gives us better resolution than we can with a high-performance spectroradiometer. We have repeatability of 0.01 nanometer resolution, which historically I would not even report because it's not a significant digit for most spectrometer systems, but we actually have that type of repeatability and stability using a photodiode-based system with optical filters built into it. So it's a proprietary design that we've come up with. There's no diffraction grading. There's no array of pixels, CCD or CMOS anywhere. It's just 3 photodiodes with specialized optical filters on top of them. So we also offer what we call our RS-7-2. So this particular configuration uses a modular version of the electronics, which are in a low profile enclosure. And what we can do here is actually attach 1 up to 4 of these sets of electronics onto a much larger integrating sphere. And in this case, the port there is 300 millimeters, so it's a very, very large output port. If you need that for your particular field of view of your given lens or sensor system. And that 300 millimeter port actually has greater than 99% uniformity, so that large integrating sphere does a great job of mixing and providing spectral and spatial uniformity. And as I mentioned, the modular light sources basically allow you to boost the output power. As you can imagine, the larger integrating sphere attenuates some of the signal, so by putting on up to 4 sets of electronics, you can get your power levels back up. We can offer this type of configuration in other size integrating spheres as well if necessary. We also offer an RS-7-3, which is a fiber optic configuration. So this couples our LED array into fiber optic probes. This is typically a customized solution for a specific customer application, so we can provide multiple outputs from 3 up to potentially 6 or even more depending on how much power is required. And we've also done things like providing collimating optics at the output end of these or other type of configurations with the fiber. RS-7-4 is our wafer prober configuration. So this particular system, again, uses our low-profile RS-7 electronics. And what it allows us to do is integrate into a wafer prober test system such as a Teradyne IP750 or National Instruments type wafer testers or any other type of brand just with a little bit of collaboration. This gives a brief system overview of how we would integrate that modular light source into a wafer tester through the test head illuminating the prober below. And the API would come certainly into play here because you'd be integrating with a larger system. So a major advantage for this compared again to the traditional tungsten halogen approach, primarily with regards to the long lifetime and the fact that we can switch much faster between different output powers. So the dynamic range adjustability without having any sort of moving parts is a major advantage. And we're able to customize and configure it for a variety of different sensor test systems. We've done this in the past with previous generations of our products, which you can see here, where we've integrated the RS5 and the series into different light sources. Here we have the Baffle tube version, the RS-7-5. So in this configuration, we are providing a larger output port, 150 millimeter diameter, and it has adjustable F numbers, so you can actually remove or add different tubes to change the F number of the optical system for your irradiance mode measurement. And then a very new model that we just have come up with, a very kind of novel optical design, is actually for wide field of view applications. So there's a variety of new lenses and devices coming out which have a very wide field of view for their optical system, and that allows or requires for a flat field something where you have a uniform flat field out to 180 degrees. So this particular device has a different approach to the optical cavity, which allows us to provide a very, very uniform flat field even at very oblique angles up to 180 degrees. So overall, just a brief wrap up here. This SpectralLED RS7 is what we believe represents the next generation in calibration and light source technology. There really isn't anything else on the market that compares to it in terms of quite a variety of the key features, namely total output power is much brighter than anything else on the market. We have quite a few more channels than the nearest competitor, so our standard LED set includes all 35 of these optical channels. You don't have to pick and choose. We give you everything, and the thermal control, optical feedback, and the linearity of our constant current driver allow the accuracy really to be unsurpassed by any sort of traditional approaches that have been on the market. So it also allows you to tune the spectrum and the color quite easily. So in some cases, it might even replace a scanning monochromator for spectral responsivity type of applications. Just makes it a very versatile and accurate tool. And we have a long history of partnering with our customers, and leveraging our existing hardware really allows us to provide quick and superior solutions for any sort of illumination-based requirements. So just because we don't have a standard model that is exactly what you need, we can quickly use what we've got on the shelf and couple it into whatever type of optical configuration might be required. So that wraps up my presentation here. So I believe at this point we can move into some of the question and answer session.
Yep, so, that's right. So I will take over. This is John. Thank you, Trevor. We're now in the Q&A portion of the webcast. So once again, to ask a question, click on the Ask a Question icon in the presentation window. I would like to mention that we've already received many more questions than we'll be able to answer. All these questions will be sent to Trevor, so he can then respond to them later at his leisure. So let's move on to the first question. Can you make a custom? Oh, are you ready there, Trevor?
Sorry, go ahead, John.
Okay. Can you make a custom LED configuration?
Yes, so we absolutely can customize the LED set that is provided with the device. So we've tried to provide a very versatile and generic set with our 35 channels, but if you need to add a particular wavelength or potentially you need more energy at a few given wavelengths, we can remove some channels, add other channels back on. So that's certainly possible for us.
Okay. How often does the equipment need calibration?
So we're recommending a 1-year calibration cycle, which is basically to adhere to our NAVLAP ISO 17025 accreditation. But within that 1 year, there's no limit on the number of hours that you can run the device. So unlike the tungsten halogen 100-hour lifetime or 1 year, in our case, you could run it continuously for the entire year and still have a very high confidence in the output power.
Mm-hmm. If the drive current is altered, the spectral content can change despite the total luminous intensity being constant. Is there an integrated spectral feedback?
So there's not an integrated spectral feedback in the traditional sense that we don't have a spectroradiometer in it, but the way that we perform our calibration, we actually know the integral energy under the curve for any given channel, and so we correct for the spectral responsivity of the optical photodiode based on whatever given channel is being illuminated. In that case, it is an integrated spectral adjustment. And as I mentioned, we also have the upgrade, the wavelength monitor system, and what that would allow you to do is check each channel individually for the centroid wavelength and further improve your confidence that nothing has drifted or changed since the calibration occurred.
Okay, so I think we have time for 2 more questions. Are you correlating LED wavelength with drive current because you are temperature controlling the pack? Isn't wavelength typically correlated to device temperature?
So we're relating the wavelength to the drive current because regardless of our temperature control, the die junction is still going to have some small temperature change. And so driving an LED with 10 milliamps of current versus driving it with 1 amp of current, even though the substrate is under very, very tight and accurate thermal control, there's still a difference in the peak wavelength, the nominal peak wavelength. So all of that is built in to the characterization, the calibration process such that the lower power levels have their own spectral power distribution data versus the higher power levels, so that at any given point we know what power level we're at, so we also know the spectral power distribution associated with that drive current. Okay,
and last question, and as I mentioned, all the other questions will go to Trevor, and he can answer them whenever he wants later. This is the last question. Can you describe the RS7 shortwave infrared 800 to 1650 nanometer version?
Absolutely. So we're currently in development of a shortwave infrared unit. We are integrating an extended InGaAs photodiode feedback into that system and basically replacing all the visible channels with shortwave infrared channels. So that new device we expect will be available right around the beginning of the new year in 2018, and will essentially cover the shortwave infrared region with similar capabilities to what we've shown here in the visible and near IR. So that particular device we're quite excited about because it opens up a whole new range of applications with different detector technologies and materials. So very much looking forward to introducing that to the market and working with some new customers.
Interesting. So that does it for the Q&A session, but I would like to ask you if you have any closing remarks you'd like to make?
I'd just like to thank everyone for their time. I really appreciate taking the time to join us, and I know that everyone is quite busy. So if you have any questions that you've posted here, we will certainly answer all of them, and feel free to contact myself directly if you want to further the discussion. We're here and ready to talk.
All right. Well, on behalf of Laser Focus World and Penwell Corporation, I would like to thank today's speaker, Trevor Vogt of Gamma Scientific, for today's presentation, a tunable LED light source for camera and image calibration. And as I noted before, for those in the audience who want a copy of today's slides, a PDF of today's presentation is available in the Event Resources section below the Q&A box. This presentation will be archived within 24 hours and can be reached from our homepage at www.laserfocusworld.com. A reminder email message will be sent to all registrants, complete with a direct link to the archive. We thank you for joining us today and look forward to serving you with future webcasts.